Take a deep breath. Feel the air fill your lungs. Now, think about your heart, beating steadily, pushing blood through your body. The iron in that blood, the very atoms carrying the oxygen you just breathed in, wasn't made here on Earth. It wasn't even made in our sun. It was forged in the heart of a colossal star that lived and died violently billions of years before our planet even existed. The calcium in your bones, the carbon that forms the backbone of your DNA, every single one of the heavier atoms that make you, has a history that is almost unthinkably vast and violent. You are, in the most literal sense, made from the ashes of exploding stars. This isn't just poetry, it's a fundamental, staggering fact of our existence. This is the story of your cosmic origins. It's a journey that begins in an unimaginable furnace and ends with you, right here, right now, a conscious piece of the universe looking back at its own creation. This is the story of how stardust learned to think. To understand where we came from, we have to go back, way back, almost 13.8 billion years to the very beginning. In the first moments after the Big Bang, the universe was an unbelievably hot, dense soup of pure energy. As it expanded at an exponential rate, a process called inflation, this energy cooled just enough to become the first fundamental particles. Within minutes, as the cosmos continued to cool and expand, these particles combined to form the first atomic nuclei. In a brief, fiery frenzy known as Big Bang nucleosynthesis, the raw material of the universe was set. The recipe was simple, almost entirely hydrogen and helium with trace amounts of lithium. But the crucial elements for life, carbon, oxygen, iron, were nowhere to be found. For those, the universe would have to wait. For the next hundreds of thousands of years, the universe was a glowing, opaque fog. Light was trapped, constantly scattering off a sea of free electrons. But as space expanded, it cooled. About 380,000 years after the beginning, the temperature dropped enough for atomic nuclei to capture those wandering electrons, forming the first stable atoms. This moment, called recombination, changed everything. The cosmic fog cleared. For the first time, light could travel freely. The afterglow of this event is something we can still see today as the cosmic microwave background, the oldest light in the universe. And with that clearing, an immense darkness fell. This was the start of the cosmic dark ages. For hundreds of millions of years, the universe was a silent, dark expanse of hydrogen and helium gas. No stars, no galaxies, just the faint, fading glow of creation. But it wasn't perfectly uniform. Tiny quantum fluctuations from the very beginning meant some areas were infinitesimally denser than others, and in this darkness, a patient, relentless force was at work: gravity. But the gravity of this normal matter wasn't enough. The universe had a secret architect, an invisible scaffolding we now call dark matter. This mysterious substance, which makes up about 85% of all matter, formed the first great gravitational wells, pulling in the hydrogen and helium gas. Slowly, over millions of years, gravity drew this gas along vast, invisible filaments, creating a colossal structure that astronomers call the cosmic web. Where these filaments crossed, gas piled up, growing denser and hotter. The darkness had set the stage. The silence was about to be broken. Imagine a cloud of primordial gas, light years across, collapsing under its own weight. As the atoms fell inward, the core began to heat up. The pressure and temperature mounted to unimaginable levels. Then, current estimates suggest somewhere around 100 to 200 million years after the Big Bang, a threshold was crossed. In the heart of one of these clouds, it became so hot and dense that hydrogen nuclei, which normally repel each other, were forced together. Nuclear fusion ignited. In that instant, the first star was born. The cosmic dark ages began to end. A ferocious new light tore through the darkness. These first-generation stars, which we call population 3 stars, were unlike anything in the universe today. Formed from pure hydrogen and helium, they are thought to have been true giants, possibly hundreds of times more massive than our Sun and millions of times brighter. Inside their cores, the process of stellar nucleosynthesis began. Hydrogen fused into helium, releasing the energy that made them shine. But for these titans, it didn't stop there. Once the hydrogen ran out, gravity crushed the core further, raising the temperature until helium could fuse into heavier elements. 3 helium nuclei smashed together to make carbon. Add another, and you get oxygen. For the first time, the universe was being seeded with the stuff of life. These stars were the universe's first factories, transforming a simple cosmos into a place of growing complexity. As more of these giant stars ignited, their intense ultraviolet radiation blasted through the surrounding gas, stripping electrons off the atoms. This process, called reionization, was the final act that ended the Dark Ages. It was a gradual, patchy affair that took hundreds of millions of years, but by about 1 billion years after the beginning, the universe was largely transparent and filled with the light of the first fledgling galaxies. But the lives of these giant stars were destined to be brief and violent. They burned through their fuel in just a few million years, a cosmic blink. And at the end of their lives, they would unleash one of the most powerful creative forces in the cosmos. The age of starlight had begun, but the age of stardust was about to be born, in a blaze of glory. The life of a massive star is a constant battle. Gravity is always trying to crush it, while the outward pressure from nuclear fusion in its core pushes back. For millions of years, these forces are in balance. As the star ages, its core becomes a layered furnace, like a cosmic onion. Hydrogen fuses to helium in the outer layers. Deeper down, helium fuses to carbon and oxygen. Deeper still, new elements are forged: neon, magnesium, silicon. The process continues, creating heavier and heavier elements until it reaches iron. And with iron, the star hits a catastrophic dead end. Fusing every element up to this point released energy, which is what held gravity at bay. But fusing iron doesn't release energy, it consumes it. Iron is ultra-stable. It's the end of the line. When the star's core fills with iron, its furnace goes out. Suddenly, the outward pressure vanishes. The battle is over. Gravity wins, and it wins instantly. The core collapses in on itself with breathtaking speed. In less than a second, a region the size of a planet is crushed down to the size of a city. The temperature skyrockets past 100 billion degrees. Atoms are squeezed out of existence as electrons are forced into protons, creating a sea of pure neutrons. This rapid collapse triggers a titanic rebound. The star's outer layers, still falling inward at a fraction of the speed of light, slam into this new, unyielding neutron core and bounce back. A shockwave of unimaginable power tears the star apart from the inside out. This is a core collapse supernova. In a few moments, the explosion releases more energy than our Sun will in its entire 10-year lifetime. But it's not just the energy. The fusion inside a star can only make elements up to iron. So where do things like silver, gold, or the iodine essential for your health come from? They are born in the hellish fury of the supernova itself. The blast wave unleashes an insane flood of neutrons. In this chaos, atomic nuclei are bombarded with neutrons faster than they can decay in what's called the rapid neutron capture process, or R process. Nuclei swell up with neutrons, becoming unstable, then rapidly decay into new, heavier, stable elements. It is here, in the final death throes of a massive star, that a significant portion of the elements heavier than iron are forged and then violently flung into space. The star dies in a final spectacular act of creation, scattering its newly minted elements across the galaxy. For many massive stars, the supernova leaves behind that collapsed core, a neutron star. A neutron star is one of the most extreme objects in the universe. It's a city-sized ball of neutrons with more mass than our sun. The density is staggering. A single sugar cube of the stuff would weigh as much as all of humanity. A good number of massive stars live in binary pairs, and if conditions are right, this can lead to two neutron stars orbiting each other, locked in a gravitational embrace. As they orbit, they stir the fabric of space-time itself, sending out ripples called gravitational waves.